Okay, hello everyone. So today we will talk about the last week assignment 12 question paper, previous year question paper for the nuclear and particle physics course. And this is the last class. Actually, not last class because after that there will be one like regarding exam and all. There will be a extra class for that. Maybe it will be on Friday itself. I mean next Friday 6 to 8 the same time, but I'm not sure right now because they did not send me any confirmation of that right now. But yeah, like officially this is the last class, assignment 12, week 12. But the main thing is that whenever I saw the last year week 12 question paper, that was totally covered whatever I did in that week 11. So maybe, I mean, similar to that one, I will add some question here, but it will be very similar, not exactly whatever it was there in the previous year assignment. Okay, so let's start. And this will be simply a wrap up thing because obviously this is the last assignment last week, so obviously all of you know all these things, so that's why I will just add a little bit small simple questions in that last week. So the and one more thing I just want to tell, like previously there were two questions, so we were having some problem, like in that recent year assignment question, there were two questions which had the wrong answer and all. So I just informed that one to Professor Paulus, and he told that he will cross check that one, and after that he will get back to me. So that was the last week answer, but right now he messaged me again, and he told that yes, that was whatever you told, these two answers were wrong, so we will re-evaluate that one. So don't worry about all these things. So whenever it will be a correct answer, that you will give the full, you will have the full marks, or if it is a wrong answer, then like if the problem is from their side, then also you will have the maybe some full marks or some re-evaluation will be there. I don't know how they will re-evaluate, but the main thing is that he said that okay, yes, it is the wrong one, so we will cross check again, and after that we will re-evaluate that one. Okay, so yeah, so start. So question number 1, select all the correct statements about quarks from below. So see, this type of questions were there from the previous year week 12 as well, it was there, but obviously that was different question, but I just put it here in the different way so that this idea should be similar, that is the thing. So select all the correct statements about quarks from below. It's a very simple and elementary question. Quarks are elementary particles with fractional electric charge. That is exactly correct because quarks have charges like 2 by 3e minus 1 by 3e something, right? So if I write here up quark, then it is like 2 by 3e. If it is down quark, then it is 1 minus 1 by 3e. So the first one is correct. There are six types of flavors or of quarks in the standard model. Yes, there are 6 types because U, B, C, B, no, C, S, T and B. So there are 6 types, 6 flavors. Okay, that is fine. Quarks can exist freely in nature as isolated particle. No, that is not correct because quarks cannot exist in freely nature. It should be confined in some form. Okay, like inside the nucleus or inside basically inside the proton, neutron, or inside any type of hadrons and mesons also. So it cannot exist freely in nature as isolated particles. Quarks interact via the weak force, but not via the strong force. That is also not correct because quarks interact with weak force. That is fine, but they said that it is not via strong force, not via strong force. That is not correct. Okay, so these are the very simple questions. So from this case, we can say that A and B are the correct one. Okay. So now coming to the second question, it's a very simple question, so obviously it's already done. Select all the correct statements regarding the Higgs boson. So the similar one is there. So Higgs boson. Let me see what is the correct answer. The Higgs boson is a scalar particle with spin 0. Yes, that is fine. That is exactly That is exactly correct one. Higgs boson is a scalar particle with spin 0. The Higgs field gives mass to fermions and bosons through spontaneous symmetry breaking. Yes, that is also correct. I don't think that Professor Paulus had discussed about the spontaneous symmetry breaking in much detail. But the main thing is that Higgs field is useful to give the masses to fermions and bosons, and the process of giving the mass to fermions and bosons are only the spontaneous symmetry breaking. In our particle physics notation, it is written as SSB, spontaneous symmetry breaking. Okay, so this is a process in which the Higgs field can give the mass to fermions and bosons. So this is exactly correct. Okay, so I'm not going to tell you the details of the spontaneous symmetry breaking process, but the main thing is that yes, this statement is correct. Now the Higgs boson was discovered at the Large Hadron Collider in 2012. Yes, that is also correct. As per I remember, I think it's 4th August maybe. The date I have to remember a little bit more. So, but the year was 2012. That is correct. And Peter Higgs was the one pioneer who got a Nobel Prize on this after this discovery. Okay. The Higgs boson mediates the electromagnetic radiation. Obviously not. Higgs boson is not a mediator in any nuclear force, right? We all know that for electromagnetic interaction, the mediator is gamma, photon. For weak interaction, W plus minus Z0 are the mediators. For strong interaction, gluon is the mediator. And for gravitational, if gravitational interaction we are taking care, then graviton is the mediator. But Higgs boson is not a mediator for electromagnetic interaction. Okay, fine. I think this week questions are very simple, but still. Actually, this will give you a whole picture of particle physics. That's why I just put it this type of questions. Select all the true statements about neutrinos. Neutrinos are neutral particles with a very small non-zero mass. Yes, that is correct. Why? Because neutrinos are obviously neutral particles, nu e, nu mu, nu tau. These three does not have any electrical charge, so it is a neutral particles with a very small non-zero mass. Yes, within the standard model, it was showing that neutrinos does not have any mass. But the main problem is whenever we saw in the experiment, that neutrinos do oscillate, and the only way to get the oscillation in neutrino sector is the result of the non-zero mass of neutrino. Whenever the neutrino will have a non-zero mass, then only it can oscillate. So that is the direct explanation, direct conclusion, or direct proof of the non-zero of having the non-zero mass of neutrinos. So yes, neutrinos are neutral particles with a very small and non-zero mass. Now, second option, neutrinos only interact via the gravitational force. No, this is not correct. Neutrinos interact via gravitational force, but it is also interacting with weak force. Basically, in particle physics language, we can say that neutrinos only interact via weak force, because we are not considering gravity in the particle physics function. So obviously, neutrinos can interact via weak force as well as gravitational force. That is not correct. The second option is not correct. Now coming to third option. Neutrinos oscillate between three different flavors, electron, mu and tau. Yes, that is correct. Because neutrinos have three flavors, electron, mu and tau, and they are oscillating themselves. Like electron, after some distance, it is transforming in muon. Then after propagating some distance, it is again transforming in tau neutrino, or it can again propagate after propagating some time, it can again oscillate into electron neutrino or something like that. So this is correct. Option number C is correct. Now coming to option number D. Neutrinos were first proposed to account for missing energy in beta decay. Yes, that is correct. So if you remember the plot, this is the plot, actually the very well-known plot. In that plot, there is a number of electrons. So there was a spontaneous symmetry. A spontaneous distribution was there. Actually, spontaneous distribution of electron means what? That means there is some problem in that angular momentum, and I mean I think all of you knows these things, so that's what neutrinos came into picture at the very first. And Pauli, who was the first one who introduces that there may be a new particle which will carry the rest of the energies, whatever make this spectrum as a continuous one, not a discrete one. So neutrinos were first proposed to account for missing energy in beta decay. That is also correct. So how many are correct? A, C and D. So this is for the neutrinos case. So till now what we have done, like let's say at the very first we were talking about all the correct statements about quarks. Then we were talking about all the correct statements about Higgs boson. Then we are talking about neutrinos. Okay, very good. Now in the next, yes, select all the correct statements about gluons. Now we will talk about gluons. Gluons are the force carriers of the strong nuclear force. That is exactly correct, because in the strong nuclear force the mediators are gluon only. And it has a color change. Gluons interact only with quarks but not with each other. No, that is not correct, because that is the difference between gluons and the photon. Photon is also massless, gluon is also massless. Photon has spin 1, gluon has spin 1. Photon cannot interact with themselves, but gluon can interact with themselves. That is the main one which makes strong interaction a very complicated one. Because in that strong interaction, gluons are mixing with each other. So this is not correct. And the Feynman diagram you can see like this one. This is gluon, this is gluon. So they both can interact themselves. Gluons are massless particles with spin 1. As just right now I told, that is correct, because it's very similar to photon. Like it is also massless, this is also massless, this is the mediator for electromagnetic, it is a mediator for strong nuclear force. And the main thing is that why we need a massless mediator. Actually the main thing is, like whenever we are thinking about mediator means what? We are going from one point to another point, and let's say in one point there is one particle and another point there is another particle, and we are going to make a bridge between these two, right? A bridge, right? So if it is a massive particle, then the distance will be little bit problematic, as we have seen in the weak force as well. For the weak force, the mediator is massive. So for this case, we can't go after certain range. So that, I mean, why we can't go? Because if we go beyond such a certain range, the mass conservation will be violated. But if it is a massless particle, there is no problem with the mass. Whenever you can go, like electromagnetic force, you know that is the infinite range. So for infinite range means what? Like if one particle is there, and let's say in America there is one particle. So India, America, there is a 2 distance. But still there can be an interaction through gamma only. Gamma only means because it's a massless particle. Massless particle cannot have any problem with the mass energy conservation. Obviously there will be a kinetic energy, but rest mass energy will not be there, so that it will be very good for our mediating particles. As a mediating particle, it will be a very good one. Okay, I just told so many things. There are 8 types of gluons corresponding to different color charge combinations. Yes, that is correct. So 8 types of gluons that we all know. So these 3 are the correct one. Okay, the 5th question is again similar to other previous questions. Select all the correct statements about the weak interaction. The weak interaction is responsible for processes like beta decay. Yes, that is correct, because the beta decay is only the first evidence of getting the neutrino, and neutrino are only, neutrinos are the particle which can only interact with the weak interaction, right? So obviously the weak interaction is responsible for processes like beta decay. W and Z bosons mediate the weak interaction. That is exactly correct. W plus W minus Z0. The weak force is weaker than the electromagnetic force but has a longer range. Okay, this you can see. weak force is weaker than the electromagnetic force. This term is fine, there is no problem. Obviously weak force is far weaker than electromagnetic force, but it has a longer range. That is not correct. Weak force has a certain range, but electromagnetic force has a very long range. So this statement is not correct. The weak force violates parity symmetry. Yes, the weak force itself violates parity symmetry. So that is correct, because you can see that like V minus A theory is there, where parity will be violated, explicitly. So weak force is the one which violates parity symmetry. But other forces like electromagnetic force, gravitational force, strong force, these all conserve parity symmetry, but weak force does not conserve parity symmetry. Okay, so maybe I can write here A, B and T. Okay, A was what? Okay, so then maybe we can go to the sixth question. Yes. Okay, sixth question was little bit like similar to the second question. Maybe I think second question of the previous year assignment. So let's have a look. The process E plus E minus going to W plus W minus is not possible. Okay, the process of E plus E minus W plus W minus. So I can see here there is no problem in the charge, there is no problem in lepton number as well, there is no problem in the like lepton number, baryon number, charge, angular momentum. These type of things will not be problematic. But now we have to see that energy momentum conservation will be there or not to have the process. So the process E plus E minus going to W plus W minus, where W plus denotes the W boson with mass 80 GeV by c square, is not possible because the mass of W plus minus is larger than that of an electron. This type of statement is not correct, because yes, obviously I understand that rest mass energy of E plus and E minus are very small than W plus W minus, but let's say if the kinetic energy of E plus and E minus is such a way that total energy of E plus E minus is exactly similar to total energy of W plus W minus, then the process is fine, no problem. So the first one is not correct. Possible with sufficiently large center of mass energy for the electron and positron. That is the one what I told. So that is correct. Possible, obviously it can be possible with sufficiently large center of mass energy for the electron and positron. Okay, the C1 possible even at low energy electron and positron energy due to quantum tunneling. No, that is not fine, because quantum tunneling is not, quantum tunneling is fine, but we have to see the energy momentum conservation in every nuclear reaction. But in this nuclear reaction, if the electron and positron has very low energy, low kinetic energy, and their rest mass is again a very low, so obviously this example will not gonna happen. Okay. Not possible because W bosons are massive spin 1 particles while electrons are spin half. No, that is also not correct, because you can see if it is spin half particle, this is also spin half, and this is, let's say, 1 1, but still there is no problem on that. Like the total energy, total angular momentum is 0, 1 or 2, and here also the total angular momentum will be 0 and 1. So that is fine, no problem, right? So only the correct option will be B here. Possible with a sufficiently large center of mass energy for the electron and positron. Okay. So if you have any doubt, you can ask me. I am just going a little bit quick, maybe, because these were already discussed in the previous or previous to previous classes. But yes, if you have any doubt, obviously you can ask me. Okay. The reaction E minus plus P plus going to N plus nu E can occur when, okay, let me write here the interaction first. This is the interaction. E minus plus E plus is going to neutron plus neutrino, electron neutrino. Now we have to check the lepton number first. Lepton number is minus 1 means plus 1, 0, 0, 1. Baryon number 0, 1, 1, 0. So that means you can see that baryon, lepton, and charge is also fine. Plus minus 1, plus 1, 0, 0. The kinetic energy of the electron is high enough to overcome the mass difference between the proton and neutron. Okay, this we have to think a little bit, but first come to the different. Okay, come to the fourth option. This reaction cannot occur as it violates charge conservation. No, that is not correct because it's obviously charge conserved. Minus 1 plus 1 0 0. The initial state electron is highly relativistic. Okay, that also we have to see. It is mediated by the exchange of a W boson in the weak interaction. That also we want to see. Okay, fine. So, I just want to write here explicitly. Now, first of all, we just want to see the energy. I mean, rest mass energy. So, rest mass energy for electron is like 0.511 MeV. I mean, okay, 0.511 MeV. This is of the order of, let's say, of the order of 1 GeV. This is of the order of 1 GeV, but like it's a little bit greater. Like mass of N is greater than mass of P because it is like 939 MeV. And it is like 938 MeV. I am obviously saying that there is some decimal points, but I am right now ignoring these decimal points. But the thing is like, it is 0.511 MeV. This is 938 MeV. This is 939 MeV, and the rest mass energy, of neutrino is 0, right? Or if it is, there is some values that is very, very small, right? 0.0000001 or something like that in MeV unit. So now you can see, if I just add these two, I mean in rest mass only, I mean we are just thinking that electron and proton are in rest. 0.511 plus 938 MeV, and here it is 939 or something of the order of 939 MeV only. So now you can see, if I write here this one, then it is like 938.511 MeV, and here it is 939 MeV. So obviously the right hand side energy is much larger, I mean not much larger but still larger than the left hand side in the rest frame obviously. But let's say our E minus has a very high kinetic energy, and very high kinetic energy to overcome this problem, to overcome this mass difference, then the interaction will be possible, right? That is the thing it is already saying here. The kinetic energy of the electron is high enough to overcome the mass difference between the proton and neutron. So I know that proton and neutron has a little bit mass difference. It should be compensated. It should be compensated by the kinetic energy of the electron. So if the kinetic energy of the electron is high enough to overcome the mass difference, then it is fine. No problem. Okay? Okay. Now coming to the next one. It is mediated by an exchange of a W boson in the weak interaction. Now let's have an assumption that E minus plus P plus going to N plus nu E. This interaction is going to happen because the kinetic energy of the electron is much larger to overcome the mass difference between proton and neutron. So this is going to happen. So how it will happen? How it will happen means, let's say I am writing the Feynman diagram here. Electron is coming. So if electron is there, to conserve the lepton number, obviously nu E will come out with this vertex only. Then there is something mediating, and then P is coming and N is going. Now you can see there should be a W, otherwise this is not a charge conserved vertex. There is minus 1 coming, there is 0 going. So let me write here, there is a W minus coming outside, and it is P plus, W minus is coming, then as a whole the charge is 0 and the neutron is charge 0. So this interaction is mediated by W minus. I mean W minus, W plus is depending on the direction only. It is mediated by the exchange of a W boson in the weak interaction. That is correct. And obviously it will be weak interaction because neutrino is present here. Okay. The initial state electron is highly relativistic. Now see, initial state electron, whatever this one is there, we told that should have some kinetic energy to compensate this problem in that mass. But it is not necessary to have the relativistic electron. Relativistic electron means it has very high kinetic energy. we don't want that much high kinetic energy, right? So it's not highly relativistic we want. So the correct option is A and B. And if you want to know exactly how much kinetic energy one electron should need to have this particle, to have the reaction done, you can just do the energy momentum calculation. That's it. As I just do here. So this one and this one. So this one minus this one, that much kinetic energy our electron should need. So obviously it's not that much high, 938.511. So it's like 0.5 MeV. So 0.5 MeV kinetic energy we need for electron. So it's not a relativistic particle, right? So that is the thing. Okay. Yes. So question number 8. The process mu minus going to E minus gamma, forbidden in the standard model without neutrino mixing, allowed if the energy of the mu1 is larger than the rest of mass of the electron and photon, possible with additional loop level Feynman diagrams involving the Z boson. Not possible because the photon is massless and the energy conservation cannot be satisfied. Okay, let me see one by one. First of all, if you see the interaction, mu minus going to E minus gamma, that is not going to happen. Why? Let me write here LE. LE is 0. This is 1. This is 0. So, delta LE is not equals to 0. Similarly, L mu 1, 0, 0. Delta L mu is also not equals to 0. Lepton number is violated. If in any nuclear reaction lepton number is violated, then obviously this interaction is not going to happen. Okay? So lepton number is violated, so this interaction is not happening. So how? Forbidden in the standard model without mixing matrix, neutrino mixing, that is the correct one. Why it is showing that neutrino mixing, without neutrino mixing, that is forbidden? See, actually mu minus going to E minus plus gamma, that is not correct because there is, if I was talking about LE, there was 1, but there should be some minus 1 term because here it is 0. So minus 1 means there should be some nu bar term. And if I want to talk about L mu, then this is 1. So there should be something, let's say nu mu, which will give us 1 in the right hand side. So neutrino mixing is not present here in that interaction. That's why the interaction is not gonna happen. Okay, allowed if the energy of the muon is larger than the rest mass of the electron and photon. Obviously it's totally forbidden, so there is no question of allowed and all. Possible with additional loop level Feynman diagrams involving the Z boson, that is also not correct. In 3 level itself it is not going to happen. Not possible because the photon is massless and the energy conservation cannot be satisfied. No, see here it is showing that not possible because the photon is massless. That is not correct. Obviously it can possible through the mass energy conservation, but the main problem is in that, just a minute, but the main problem is with the lepton number conservation. So that is the thing. Okay, so that is also fine. So the main option is B. Other B, C and D options are totally wrong. Okay. Now we can come here. The decay T going to be W plus is possible. Okay. T going to be W plus. Possible with large probability in the standard model. Not possible because the top quark has a greater mass than the bottom quark. Possible through the weak interaction mediated by the W boson. Forbidden due to the top quark being a fermion and the W boson being a boson. Okay. Let me see here. Top quark, bottom quark, W plus. At the very first, let me write here Q. This is 2 by 3 E. This is minus 1 by 3 E plus E. I mean 1e, right? So this is like minus 1 plus 3, that means 2 by 3e. Charge is fine. Baryon 1, 1, 0. I mean 1 by 3, 1 by 3, 0. So baryon is also fine. These two are not lepton numbers. I mean any of these three are not lepton. So obviously lepton number is also fine. Now mass. Mass of T is very large than mass of D, as well as mass of W plus. Now we can say that from the mass conservation it is also fine. Even T going to BW plus, this is the very common tau decay into the standard model particle. So possible with large probability in the standard model, that is correct. Not possible because the top quark has a greater mass than the bottom quark. Top quark has a greater mass than the bottom quark, that is fine. But what is the problem with that? That should decay in the lower mass state, right? So option B is not correct. Possible through the weak interaction mediated by the W boson. Yes, that is correct. Because we can see here that top quark is going to bottom quark through W plus. So, possible through the weak interaction mediated by W boson. It's correct. Forbidden due to the top quark being a fermion and the W boson being a boson. That is not correct, right? Because T is a fermion, B is also a fermion, W plus is a boson. So, if it is half, this is also half, spin if I am talking, and this is let's say 1. So, what is the problem? This will be like half, 3 by 2, and here it is half. So this is fine. So only the correct option will be A and C. Okay. Yes. So question number 10. The process PP going to H plus X. X, oh, okay. I did not mention here. X is any additional particle. I mean it can be anything, any additional particle. Only possible at energy levels exiting twice the Higgs boson mass. Okay, let me write here P plus P going to H plus X. Now we can see the mass of H is like obviously 125 GeV. Mass of proton is of the order of 1 GeV, 1 GeV. So it is like of the order of 2 GeV. And it is 125 GeV, and there should be some mass of this one also. But what they are telling, only possible at energy levels exceeding twice the Higgs boson mass. Why we need twice the Higgs boson mass? Let's say, I don't know what is X, but let's say this has a 50 GeV mass. Then as a whole, I mean I am talking about only the rest mass here because we are assuming that this H and X are in the rest right now. So as a whole it is like 175. But they are telling, okay, so if 2 GeV is there, so 175 minus 2 of the order of 173 GeV they need. But in that first option they are telling that no, 125 into 2, that means 0, 5, 2. 250 GeV we need to have the process, but it is not correct. Okay, this is not correct. Allowed with high probability at the Large Hadron Collider. The main thing is that, yes, that is correct, but like PP going to H plus Ax, that is correct, that it has a high probability at the LHC level, because in the LHC level, the probability, the energy of the proton is too high, like of the order of TeV, okay, like 7 TeV, 7, 7, 13, actually the root over S is 13 TeV, something like that. So it is fine that it is allowed with high probability at the LHC, but always it's not the exact answer, okay. But still we can, allowed means partially it's correct. This statement is partially correct because it's allowed, but it is not like that in any other nuclear reactor or any other experiment it is not going to happen. It will happen when the proton will have that much energy. That is the thing. Okay. Forbidden because protons are made of quarks and Higgs bosons only coupled to massive fermions. No, this is not a valid statement. Protons are made of quarks and Higgs boson only coupled to massive fermions. That is what is the problem with that? Massive fermion is, quark is also a massive fermion. So Higgs can interact with the massive fermions and it can interact with quarks as well. So this is not correct. Allowed through the gluon fusion mechanism where gluons inside the protons create the Higgs boson. Yes, that is correct. Actually, what is gluon fusion mechanism? That we need to think a little. Hello? Hello? Are you telling something? Anyone? I'm audible, right?
Yes, ma'am.
Okay. I don't know. Maybe someone was talking something. Okay, if you have any question, you can unmute yourself and tell. No problem on that. Okay. What I was talking? Yeah. Allowed through the gluon fusion mechanism where gluons inside the protons create the Higgs boson. This option is correct or not, that we need to check. The interaction was like that. Okay. So what is there inside of this interaction? There is one proton. Proton means obviously UUD. And there is also UUD. And there is Higgs boson. And in Higgs boson means boson are the, there is no quark level things. And there is some particle. I don't know about this one, right? So gluon fusion mechanism is the one which makes these quarks to Higgs. How it is making? Actually, it is these two will come and they will make a top quark. Top quark means, obviously, like how to make a heavy Higgs than a UUD, because heavy Higgs means 125 GeV is the mass of Higgs, right? And UUD, these three individually, if I want to tell the mass, that is less than 125 GeV. But obviously, to produce 125 GeV, we need a more massive quark. Other than how can it be possible to produce Higgs, right? So basically, in the quark gluon mechanism, what they are telling in the quark gluon mechanism, I am not going to tell the details of this, but the main thing is that the proton-proton, they are interacting, and proton-proton means obviously inside the quark level they are interacting, and after interacting in the quark level, that will produce a little bit somewhat of, obviously some other quarks will be there, but the main quark will be in top quark. And top quark, you know that top quark has a very high mass and it will definitely produce a Higgs. And obviously I am not talking about right now X, because we don't know about X right now. What is X? That is also we don't know. That is simply additional particle. So allowed through the gluon fusion mechanism where gluons inside the protons create the Higgs boson. How it is creating Higgs boson? After creating tau boson, it is creating Higgs boson. Tau quark, it is creating Higgs boson. So that is correct. So option number D can be the correct option. All other options you can see A, B, C, these are not correct. Actually B is little bit partially correct but not exactly correct. This is the LHC is not the only ultimate experiment which can produce PP going to H plus X. There may be some other experiment in future also which can be processed, which can have the larger kinetic energy of proton, which can make H plus X with a very high probability. That is also fine. So only the D option is the correct one for this case. Okay, maybe we can go to the next one. Yeah. Actually, today I think I have 15 questions. So this is question number 11. So maybe, okay, fine. There will be so many time left. Fine. Particle Y decays to two particles, C and D. Hello? You are talking something? Okay. So particle y decays to two particles C and D. So here it is like that y is coming as C plus D. If y and C are bosons, then D is what? Okay, it's very similar to whatever we did in the previous class also. So y and C are bosons. So bosons means, let me write here spin. Because boson or fermion is totally, I mean like the main difference between boson and fermions are the spin, right? Bosons are the integral spin and fermions are the half integral spin. So spin for y is why they are telling it is a boson. So y has a boson, that means let's say 0 or 1, let's say 0 or 1. And C is also 0 or 1. Then what about D? Obviously, let's say if this is half, then the total angular momentum will be like half. I mean if it is 0 and 1, I mean if it is 0 and half, then there will be half only, the total angular momentum. Or if it is 1 and half, then there will be two combinations, half or 3 by 2. But in the left hand side, 0 and 1 is only possible, there is no half integral spin like that. So D cannot be a fermion, D should always be a boson. If it is a boson, then what will happen? C plus D, and the spin is like, let's say 0 or 1, this is also 0 and 1. And I am thinking that this is also 0 and 1. So what will happen? 0 and 0, let's say 0 and 0 will come as 0. 0 and 1, it is also coming as 0, I mean like 1. 1 and 0 also coming as 1. 1 and 1 is coming as like 0, 1, 2. So obviously 0 and 1, it is fine. The main thing is that D should be a fermion. It is boson. It is necessarily a boson. Okay? Necessarily a fermion, it is not correct. Could be either a fermion or a boson, that is also not correct because of the spin conservation. Okay, so this is done. Yes. If particle Z decays to two identical particles E and F, and both E and F are fermions, particle Z is what? Okay, that is also similar to that one. Z is going to E plus F. E and F are fermions. So let's say it is half. Spin I am talking, okay? Spin is half. So total spin is how much? Let's say 0 or 1. So here in the left hand side it should be 0 or 1. That means our Z should be a boson. Is necessarily a boson. Otherwise, E and F are fermions and Z cannot decay to E and F. Okay? So this is the case. Oh, it's question number 12. Okay? Now come to question number 13. Similar questions are there. Okay? If particle W decays into 3 particles. Okay, it's a little bit different. Just see the question. Particle W decays into 3 particles, G, H, I. And W is a fermion. W is a fermion means let's say spin is half. Then the combination of GH and I. So how much it will be? It should be a half integral spin, right? Because the W is a fermion. So the total combination should be a fermionic like nature. 3 by 2 or half or like that. But if it is 3 by 2, then 3 by 2 should be there. If it is half, then half should be there. So the combination of GH and I should be half 3 by 2 like that. But the answer options are given in a little bit different way. How they are given? Must include at least one boson. Now see, must include at least one boson. Let me write here G is one boson. That means 0. Spin. And I am talking here that at least one boson. That means I am writing here at least one boson. I mean at least one particle Z as boson. Then H and I am talking about like let's say fermion. So these two are fermion, this is boson. I am thinking according to the option number A. Then what will be the final spin angular momentum? This final spin angular momentum will be like, with these two it will be coming as 0 or 1, and among this 0, 0 or 0, 1 it will come as like 0 or 1. But now you can see that it will not a half integral spin, what we want. So the option number A is not correct. Okay. Now come to B, option number B. Option number B was must result in an odd number of fermions. Let me write here, it is correct or not. Odd number of fermions. I told this is, let's say, half 3 by 2. And as a whole, it should be half or 3 by 2, right? So odd number of fermions, that means that odd number of fermions means, let's say at least one is fermion. One is fermion means, let's say this is half. And these two are boson. Let's say this is 0, this is 1. So as a whole, this will give us 0 or 1. I mean basically 1. So if it is like that, then it will come as 3 by 2 or half. That is fine because we are having the same one, half integral. Now see, odd number of fermions, why they are telling, let's say I have 2 fermions. If 2 fermions are there, then half, half, and the I is, let's say, 0. I mean like boson. Then the problem is 0, 1 and 0. So that will not be a correct option. Now come to all 3 are fermions. That means half, half, half. Then what will happen? This half will give us 0 or 1, and with that half, what will be the answer? It will be like half 3 by 2. So that is fine because we are having in the left hand side again half 3 by 2. So one fermion is also fine, 3 fermion is also fine, but 2 fermion is not fine. So whatever they are telling must result in an odd number of fermions, that is correct. Okay, now see the third option. Could be either all bosons or a mixture of fermions and bosons. This option is correct, mixture of fermions and bosons. But could be either all bosons, that is not correct. Why? Because if all the particles are bosons, let's say 0, 0, 1. So this will give us 1. So as a whole, it will give us, let's say, 1. So if it is 1, then this is the fermion, so it will not the correct one. So only B option is the correct one. Okay? Okay. Yes, now come to this question. Particle P decays into x plus y. If P is a fermion means half, spin half, or 3 by 2, whatever. The combined spin of x and y must be 0, must be an integer, must be a half integer. That is obviously all known, that should be a half integer. Otherwise, the left hand side and right hand side should not be the correct one, equal one. So if P is a fermion, then must be 0 is not correct, must be integer is also not correct, must be a half integer. Okay. Now maybe this is the last question. Yes, this is the last question. Okay. A particle Q decays into a photon and a fermion. Fermion, let's say I am writing here P. Q is a fermion. Okay. So Q and P, these two are fermion. The photon, there are 3 options. Okay, this is a little bit interesting question. So just let me give some time on that. We have fermions as Q and P. So the spin of Q is like, let's say, half, because it's a fermion. Spin of P is also half. Now gamma is photon, right? Photon is a boson, we all know that, and it has a spin as 1. So if I write the total angular momentum, then it will be like half or 3 by 2. So that is fine, because in the left hand side there is half, in the right hand side half and 3 by 2 is coming. So the gamma should have an integer spin so that the interaction will be fine. I mean, by seeing the angular momentum conservation, right? Now see the options. Photon is necessary for the decay to conserve energy. Okay, is it correct? Q is going to gamma plus P. We don't know about P, we don't know about Q. Let me assume that mass of Q is equal to mass of P. Then, I mean total mass of Q is equal to total mass of P. If it is like that, then we can say definitely we don't need gamma here to conserve energy. I mean, energy momentum conservation will be fine without the presence of gamma also. So whatever the option is giving here, photon is necessary for the decay to conserve energy, that is not correct. Yes? Because it can be decay to P if mass of Q is greater than mass of P, I mean rest mass, so that it can decay directly with something, or it will have some kinetic energy with that. But total mass of Q is equal to total mass of P. If this is true, then we don't need any gamma. But the first option is not correct. The photon is necessarily massless. Yes, photon is massless, but it is not directly related to this interaction. In this interaction, Q going to gamma plus P, actually gamma is needed to have angular momentum conservation. As we have seen just before, that Q was, let's say Q is 3 by 2, P is half. Both are fermions. So in that case, left hand side is and right hand side are not equal if gamma is not present here. If gamma is present here with spin 1, only then the total angular momentum of this decay is half 3 by 2. And this 3 by 2 can match with left hand side 3 by 2. So, a particle Q decays into a photon and a fermion. If Q is a fermion, the photon ensures the decay conserves angular momentum. These two options, I mean this B option is obviously true for all the cases, but particularly in that decay, which one is necessary to have the gamma in this decay. The necessity of gamma is like that, it ensures the decay conserves angular momentum. That we need to recap, I mean that we need to think about. Okay. So what is the main advantage of getting gamma in this decay? That is giving the answer that the decay should conserve angular momentum, and angular momentum should be conserved only in the presence of gamma. Otherwise, it cannot be the conserved one. As per I told, like let's say the Q has angular momentum 3 by 2, P has angular momentum half, because both are fermions, and they did not tell about which fermion they are. So maybe it is 3 by 2, maybe it is half. So obviously only in the presence of gamma it will happen. So that is the case. So option number C is the correct option. Then is there any other questions? No, I don't have any other question. So maybe it's a little bit very early today. But yeah, obviously if you have any doubt, actually what I did here, these questions were not the previous year assignment questions. Previous year assignment week number 12 questions were already discussed in the week number 11 as well. So I was just thinking to have some basic idea about throughout all the particle physics courses, whatever it was taught in the course. So this is the thing. If you have any doubt, any question, you can just ask me. I'm just going to scroll the questions a little bit slowly so that you can remember these questions, because it's a 15 question. So that one was the last question. Now coming to 14th question. This is the 14th question. And then 13th question is this one. Then 12th question. Then question number 11. Question number 10. Question 9. Question, this is 8. This is question 7. This is 6. This is 5. This is 4. Three. This is 2. This is 1. Any question, any doubt, anything, if you have, then you can ask me. And as I already mentioned in the first half of the class, that there will be one more class regarding the question answer of the means like exam pattern and that exam like question answer, what can be the question in exam. Obviously I am not going to do the question paper for nuclear and particle physics, so I don't know exactly what type of question will be there, but important questions, important topics, I will just cover a little bit in that next class. And the next class will be most probably 18th, 6 to 8, the same time. So this is the thing for today. And do you have any problem in the present year assignment questions and all? Because we have seen that there were some problems, and obviously like it was some misunderstanding and all. So is there any problem, is there any doubt regarding the last assignment, previous last assignment, this year current assignment, whatever? If you have anything to share with me, that is also fine. If you don't have anything, then maybe we can stop the class and we will meet in the next class. And next class will be the final one. Officially this is the final one, but next class will be a just help, like there we will just talk about question pattern, what will be, how many numbers of Q&A will be there, MCQ will be there, that type of question we will be discussing in the next class. So, okay. Is there any question till now? Someone was there? Vinod? Any question?
Thank you, ma'am. Thank you, ma'am. No, ma'am.
Okay. So, do you have any problem in that current year assignment questions? As you mentioned, last two questions were problematic. So, no questions, na?
Yes, ma'am. No.
Okay, fine.
Thank you. Thank you
Okay,
very much.
okay, bye bye. And we will meet soon in the
Thank
next
you.
week. Okay,
Oh, thank you. Thank you.
bye.